Okay, so does anyone remember what was the symbol for friction up to now? What was the symbol for the F what? F capital for force, and the lower subscript would be what? Would be F. But today, we start knowing that friction can always be divided into how many kinds? Two kinds, okay? Two kinds for friction. So whenever you deal, friction is the force that either, okay? If you're trying to move something, if you're trying to move it, which means right now, it's what? Right now, it's what? It's stationary. What does stationary mean? Stationary comes from static, which means not moving, okay? So if you're trying to move anything that is at rest, that is one kind of what? Kind of friction. So it prevents a stationary object from starting to move when you start what? Applying a force to it, okay? Or an external agent applies a force to it. So that's one kind. The other kind is the kind that acts on an already in motion object, already moving object, and tries to, well, definitely it tries to slow it down. And if it could, brings it to what? Brings it to a complete stop if possible. Okay? So that's basically why we have two kinds of friction, because it depends what kind of situation we are trying to change. Are we trying to change a stationary situation, or are trying to change a situation where motion has been already happening before we start to change it? Okay? So because of that, we have two types of friction. The first one is called static friction, which means no motion. And I have to be very clear about this, okay? It will lead to some debate, which is fine. That's actually the way that things have to go. No motion yet. No motion yet. So everyone, always be sure of this. As long as you're applying motion, sorry, as long as you're applying what? You always apply a what? As long as you're applying force and the object is not moving yet, you are still in the kingdom of what? Static friction. However, once it starts moving, like right at that second, right at that, cut off moment, when it starts moving, you still what? You still consider it to be still what? To be what? To be static friction. Okay? Immediately after that, it becomes what? What's the other kind? Kinetic friction. Yes, thank you. Motion already exists. Okay? So as long as it's not moving or just started the motion, like you just observed it, you just cleared the what? The static friction. Everything after that is what? Is kinetic friction. Okay? All right. So obviously we're going to have a bunch of slides talking about each one. So let's start first talking about the static friction force. All right. Okay. Static friction. So what is the definition of the force of static friction? It's the force you go against when you try to move a stationary object. When it tries to move a stationary object. Obviously, friction has to exist from what? Or has to come from what? From already existent traction between two surfaces. That's why if you're on ice, it's very easy to move absolutely anything on ice. Why? Because there's barely any friction. Which means what? Which means Newton's third law says you just need a very small force to move it, because there's almost no force what? Acting on the object from the traction on the two surfaces. Okay? Okay? All right. Now, the physical symbol for the maximum. Okay, so everyone, this is an important idea about what? About static friction. Okay, static friction. Whenever we talk about static friction, we always pay attention to what? To the maximum amount of static friction, which is basically what you really need to up your force until you start what? Until you start getting the object to move. Exactly. So the physical symbol for the maximum static friction force is, who remembers it from grade 11? Same exact symbol. Fs. Yes. Fs. Why do you think I don't need an arrow? Because friction always goes what? With or against the applied force? Always against the applied force. It never goes with motion. It always wants to go against motion. Okay, so Fs, no arrow needed. Obviously, you're going to give me an FBD, so there you go. You just gave me the diagram and the direction. Okay? Okay. Whenever you deal with friction, you don't just deal with the force. You also deal with something called the what? Called the coefficient. How many of you have heard of the word coefficient before? Where do you usually hear it? In what kind of course? In a math course, exactly. Coefficient is just a fancy name for what? For a value or a number that's associated with an equation. Okay, like when you deal with a quadratic equation, for example, you always hear about the quadratic coefficient, which is the coefficient or the number stuck next to the x squared, the linear coefficient, which is the number stuck to the x, and so on and so forth. Okay, so there's a very specific number called a coefficient that is associated with static friction. It is called but nothing but the coefficient of static friction. That's the official scientific and official name for it. Okay, now who remembers the symbol for these things? We had to go to another language. It's not an English symbol. Does anyone remember it from grade 11? Greek, actually, which is, again, I mean, half the words and symbols in physics or science are either Latin or Greek. Second, mu. Yes, mu, which is the Greek U. Okay, alpha, beta, gamma, delta. You keep going until the end. You hit mu. How do you write mu? Like this. Okay, so the easiest way to write mu is just to write as if it were a U. As if it were a U. By the way, I know some of you will take the easy way out and basically do a shortcut and just write a U. No, you can't just write a U. It's mu. Has to have this right here. Or you can just go like this. Just make sure it doesn't look like an M, because oftentimes you will actually write it like that. No, please make sure that it looks like, I'm not going to take marks off if it comes out like that. Trust me. Relax, okay? But please, for future courses, just go like that. Okay? That's all. That's what mu is. All right? We're not going to be dealing with a lot of Greek symbols in this course, but we need to know that they will actually make their way to a lot of things. Okay? So the coefficient of static friction is called what? Mu s. Mu s. Okay? Pronounced mu s. Okay? All right. Equation. Or until you finish copying. Okay. So the defining formula for the coefficient of static friction is, okay, everyone, this is, if you do any kind of physics or engineering, this is always got to be the equation of what? Of the coefficient of static friction. Of the coefficient of static friction. We will actually be doing, I haven't decided when we're going to do labs yet, but whenever we do any lab with friction, this is how they always what? Calculate the coefficient of static friction. All you have to do is divide two things. You divide the what? The maximum static friction force, or basically just the amount of force that it took you to start moving an object, and you divide by what? Normal force, or how much is the surface pushing up on the what? On the object itself. So the two ways of usually doing this equation is either writing the equation this way exactly, which is basically this equation. However, oftentimes you might need to rearrange it, which basically, can someone tell me how to go from this equation to this one? What was the only thing you did? Cross multiply, exactly. There's an invisible one here. There is an invisible one here, and you crisscross. So one equation gives you what? One equation gives you technically the value of the coefficient of friction by dividing the Fs over the Fn. The other equation gives you the Fs, which is the actual amount of force you need until technically that was very easy to move, but until you start what? You start moving something, which is multiplying how much mu s times how much the Fn is as well. Okay? All right. What kind of properties does any mu s have? Well, three of them. Number one, it has no units. Absolutely no units. By the way, this is almost the first time in physics that we talk about what we call a unitless, or in physics, the official name is dimensionless quantity. And why does it have no units? Because the what? Because the newtons here. Because this is going to be a number. And this is going to be a number in newtons. The newtons are going to cancel the newtons. By the way, very few quantities in physics have no units, but you still need to understand that they still exist. Which means, as much as I'm always telling you to remember to put what? To put units, you still have to remember that sometimes putting a unit is actually what? Is actually incorrect and actually wrong. Which means if I ever ask you, what's the coefficient of friction between, like, let's say let's say I'm trying to move this tablet, and I tell you it took, like, let's say for example 5 newtons to start to move it, and the normal force is like 20, for example. What's the coefficient of static friction? And you tell me, oh, it's like 0.37 something like newtons or meters, boom, that's it. You lose half a mark. You lose half a mark of the final answer just because you put a unit where there's no unit to be what? To be actually used. So always remember, only in very few cases, but you still have to know them. So that's the first feature, no units. Number two, it's always what? Yes, which means if you ever do the math and for some reason your mu s comes out to be negative, go back. There is no such thing as what? There is no such thing as a negative mu. Why? Probably the easiest explanation is it's a ratio between what? Between what? A force and another force. Can forces ever be negative? Okay, they could be negative as a direction, but as an actual entity, is there such a thing as a negative force? No, a force is what? Is a physical measure of how much you're trying to what? To push something. That's always a positive thing. So that's why if you're ever doing the math and your mu s comes out to be either 0 or less, go back. You have to fix your math. You can't just say, oh, I'm just going to ditch the minus in my final answer. You can't do that because remember, I always ask you to show your work and I will mark wrong any step that led to what? To the math being wrong in up to the negative coefficient. Last thing, most of the time, this coefficient is what? Less than 1. But it could actually come up to be what? It could come up to be what? Bigger than 1 or 1 itself. Okay? Because think about it this way, everyone. It basically is a ratio between how much you need to push by and how much the surface is pushing by. Oftentimes, it's what? It's what? Which means what? Which force is it usually? Sorry, like which force is bigger, Fs or Fn? If it's mostly less than 1. If you have a fraction less than 1, which one is bigger? The top or the bottom of the fraction? The bottom of the fraction, which means most of the time, Fn is what? Bigger or smaller than Fs? However, in some cases, it could be what? It could be Fs is bigger than what? Than Fn. Okay? Very few cases, depending on the roughness of the surface and how much it takes to push it. Okay? But most of the time, we're going to be dealing with what? Less than 1. So a decimal less than 1. Okay. 1 second. All right. Let's go to the next slide. Okay, everyone, pencils down. No need to copy here. The whole thing is ready for you. I don't want you to look at it. Don't read it. Let me actually talk you through the whole thing. Okay? So now, Ammar, can you read the equation for me? Everyone, listen carefully to what Ammar's going to read. Coefficient of static friction equals. What did you say? What static? Max. Max static friction. Okay. So everyone, eyes on me. I'm going to, right now, this table is moving or stationary? Right there. This is stationary. So that means what? To move it, I have to apply somewhat, some force. Okay. Let's see the veins pop. Okay. Am I pushing? I am pushing. But is it moving? Which means there has to be a what? If I'm pushing and it's not moving, according to Newton's first law, there has to be a what? There has to be a counterbalancing force, right? F net equals 0 means whatever gets applied has to have a what? This is not Newton's third law. I'm just talking about F net equals 0. If there's a force going this way and nothing is happening, that must mean there's a what? There's another equal and opposite force going that way. Okay? All right, so I'm pushing. Sorry, yeah, pushing. Nothing. So what do I have to do to my force? Keep it the same or up it up? I need to increase it. I need to take it up, up, up. And at some point, what happened? I clear the what? How many people know what the threshold means? Threshold in English. What does it mean? Threshold. It's like a what? Something that you have to cross, right? Like a step you have to cross, right? So once you clear the threshold, what happens to the object? It what? It starts to move, okay? Here's the thing. If I ask you right now, what is the Fs? You cannot give me any of the force amounts until you actually what? Until you actually what? Start to what? Start to move. So for example, let's say, so basically, okay, let me just read this. So Fs does not just represent any friction force. It represents the minimum amount you need to put in to start what? To start what? Moving things. Or in other ways, the other way to understand, it represents the maximum amount that the surface could what? could go against you. Remember, the maximum the surface goes against you is the minimum you have to what? Is the minimum you have to put in to start things what? To start things to start moving, or to get things to start moving. Okay? So for example, let's look at this. Okay. What does that mean? Right there. If you're pushing with 2 newtons and no motion is happening, how much is the friction stopping you by? Has to be what? By the way, does it make sense for friction to be going at 3? It doesn't. Okay, it doesn't make sense. Why? Because could friction ever make things jump against you? No, it either halts it or submits to you and basically what allows it to move. Okay, so right here we know has to be 2 newtons. This is not Fs, even though it's not what? Everyone, phones away. Even though it's not what? Even though it's not moving, this 2 newtons is not what? Because you don't know if you hit the maximum yet. So what do you do with your force? You keep what? You keep increasing it. You increase it to 4, yet you see what? No motion. So you still know, okay, I've got 4 newtons going against me, but I still can't guarantee this is the what? This is the value for Fs. You notice that when you push with, sorry, 6.0001 Newton, let's say, that you what? Just move. So what logical conclusion could you make? How much did you need to clear until you got to start moving? Exactly what? Almost exactly what? 6 newtons. By the way, how many people are doing limits in function or in calculus? This is the exact same idea. What's a limit? Something you keep getting what? Closer and closer and closer to until you actually what? Touch it, but it doesn't become a limit anymore. That's exactly it. The limit is basically what? Just how close can you get? So, can you say now that you can take Fs to be 6 newtons? Yes, you can, because it took that much to what? To clear the threshold. So the S 6 newtons is the value of what? Of Fs. Why? Because it's the maximum balancing, neutralizing force due to friction that you had to what? You had to go against. Therefore, the mu-s equation only gives the maximum value of opposing, preventing friction, and not just anything before that. Does that make sense now? You need to know the mu-s equation does not give you what? Anything below. It gives you the what? The exact maximum you need to clear to start moving things. Okay? All right. Let's talk about what now? The other one, which is kinetic friction. What is kinetic friction? It's the friction you go against when something like this happens. Look. From the moment I left it to the moment it stopped, it was under what? Because it was already moving, but it did come to a stop, which means kinetic friction was the one acting on it the whole time once it left my hand. Okay? So the force of kinetic friction is what? Is the force that you go against when you try to keep moving an already moving object. Just so you know, everyone, just so you know, kinetic friction is what goes against an object regardless of how it's moving. Speeding up, slowing down, constant motion, it doesn't matter. Kinetic friction just takes care of motion. What type of motion? All types of motion. Speeding up, slowing down, turning, or cruise controlling. As long as it's moving in any way, shape, or form, it's under kinetic friction, provided the surface can actually what? Have enough traction for friction. Any guesses for the symbol? I mean, Fs for 1. So what should this one be? Fk. You're absolutely right. And the good news is it's Fs and Fk no matter what engineering or physics you ever do. Those two symbols will never change. Sometimes symbols change, not these. Okay? Again, no arrow needed. Why? Because it's always going to go against you or against whatever applied force there is. There's also a what? A coefficient. It's called the what? Coefficient of kinetic friction. And what's the symbol? Mu k. By the way, I don't care if you're K or S, a lowercase or uppercase. I just have a habit of doing the lowercase for the Ks and the S. Okay? It's exactly the same slide. The only difference is different subscript, different word, and slightly a different what? A different way of saying it. Because it's now not moving a stationary one. No, it's already been moved. So now you cleared the static, and now you're in the kinetic region. Word for word, it's exactly the same slide, except for those differences. Okay, good. All right. Equation. Same thing as the what? As the static. We just got to change a few small things. There we go. Instead of static, you have kinetic. But everyone, what word is not here anymore? Max. Yes, max. For static friction, there is a maximum you have to clear. For kinetic friction, there is no max. There's one value that just keeps going against you. What? No matter what the force is. By the way, everyone, just so you know, and this is not something you need to know for grade 12, but sometimes for first year, and obviously if you major in like civil or mechanical engineering. Okay, drag actually depends on what? On how fast you go through it. The faster you go, through a medium. Actually, what? Actually, the more drag on it, the more drag you face going against it. Okay, not in friction though, or at least not in grade 12 friction. Same equation. Do you think it's the same exact three features? Raise your hand if you think so. Do you think it's the same three features as the mu s for the mu k? Yes, it is. Number one, no units. Again, units cancel out in the newtons, in the Fk and the Fn. Also, it's always positive. So if you ever do the math and you get a negative mu k, go back. Something really went bad with the math there. Number three, mostly less than one. Yeah. Yes. Go ahead. Oh, it says mu s. Sorry, everyone. Thank you. Yes, thank you. When I copy pasted, I forgot to change this one. There you go. This is K. Perfect. Okay. Nice. Anything else? Nope. We're good. Okay. Okay. Pencils down. Pencils down. Eyes on the screen. Can anyone tell me what they notice when they compare the numbers in each red box? Raise your hand if you see a trend. You have to see that trend. Sorry, no, raise your hand. Raise your hand. Josh, what do you see? Always in every red box. Say again. Mu s, the static friction coefficient, not force. Coefficient is always what compared to the mu k? 7.8, 42, bigger. 0.05 to 0.11 covers a what? A bigger range than 0.029 to 0.12. 61 bigger than 52. 0.1 bigger than 0.03. 0.1, 0.01, 22, 18, 14, 10, 01, 03. Is it ever less than it? No. Could it be equal? Which ones? I guess this one. But again, probably within what? Within experimental what? Experimental measurement error. So what do you always conclude? Which one is always bigger? Which one's always bigger? Mu s. What kind of an important conclusion does that give us? Well, if you really think about it, okay, don't copy. This is there for you. But everyone, what was the equation for mu s? Mu s equals what? Fs over what? No need to copy. No need to copy. This is just a basic comparison. Yes, and mu k is equal to what? Okay. Which symbol in these two equations is always going to be the same? Which symbol is the same in both equations? Fn, which makes sense because the surface is not going to change how it pushes up all of a sudden. Okay, Fn is going to be the same, which means if this guy is bigger than this guy and this one is held fixed, what can you tell about Fs and Fk? Which one is bigger? Exactly. If this decimal is bigger than this decimal, that means this fraction is always bigger than this fraction. And if those two are the same, then the only thing that has to be bigger is this one compared to this one. Perfect. There we have it. If mu s is bigger than mu k, by the way, you might say, hold on, wasn't it equal sometimes? Yeah, I agree. But in 99% of the physics problem you're going to see in grade 12 and first year, you're always going to get what? Or 99%, you will get a mu s problem, a problem with mu s bigger than mu k, which has to translate to Fs being Fk. So what do we conclude? Which is harder? Which one is harder on you as an applied force? To keep an object moving or to start it to move? Why? Because static friction requires more force than what? Or gives more force than kinetic friction. Yep, in other words, it takes more force to start moving an object than it does take to keep it moving at some constant speed. Which means whenever you start moving an object, everyone, think about it this way. Whenever you start moving an object, immediately at that moment, what do you do to your own force? Do you need to keep it high or can you get it lower? You can get it lower because you do not need as much Fs against you when you're going through motion. Okay?
Hello, everyone. Sorry for the interruption. We're just adjusting our bell. So please ignore it.
Oh, okay? So it takes more force to start things to move than to keep them moving afterwards. Always. So if you're ever solving for an equation, everyone, if you're ever solving for a problem, and somehow you get your mu k bigger than your mu s, or equivalently your fk bigger than your fs, go back. Go back. Okay? All right. So let's do a couple of problems before I show you some interesting animations to really show you how these equations actually work in real situations. Okay, let's go to the next slide. I think it's a demo. Yes. Okay, everyone, let's read this problem. So you are given the job of moving a stage prop, as far as you're concerned, a box, with a mass of how much? 110 kilograms across a what? Horizontal floor. The coefficient of static friction between the base of the prop and the floor itself is 0.25. How much? Calculate the what? The minimum force that you have to give, which is another way saying what? The maximum what? The maximum force of static friction that the surface is willing to what? Or able to give against you. Okay, first of all, is this a mu s or a mu k equation? Right there. Are you keeping an object moving or are you trying to move it? You're trying to move it, which means what? This is a mu s equation. By the way, the reason I'm saying that is that you will see some problems in grade 12 and first year where you're given both mu s and mu k. You're given both, but it doesn't tell you which one to use. What does that depend on? You understanding if it's what? Either what? Not moving yet or already what? Bless you. Already in motion, exactly. So obviously, we have to what? We have to use the mu s. So go ahead. Mu s equals Fs over Fn. Okay, everyone. Technically, this problem really doesn't need you to sketch an FBD, but let's sketch an FBD because sketching it will really make you understand why the next step is going to happen. So let's sketch the what? Here's the surface, and I'm sketching it to look rough, to actually indicate that there is some roughness to the surface. Here is my box. Okay, what's force number one? Always on Earth. Gravity. So go ahead. From somewhere in the center, just go down, Fg. Okay, what reacts to gravity or what counterbalances gravity? As long as there are surface, of course, there's normal. Otherwise, it would be free falling down. So Fn. Okay. Did they say which way you're pushing the prop? No, they didn't, which means I'll choose to push it to the left, which means what should be going this way? If I'm pushing, what force is that? Applied. Force applied. And since it's not moving or it just moved yet, what force was I going against the whole time? Static friction force, okay, which is Fs. I like to put it here, where it actually happened. Okay, is this a one-dimensional problem or a two-dimensional problem? No, look. Yeah, we have an x-axis and a y-axis. What can you tell me about this object on the vertical axis? Is there any indication that this object is going to sink down? Is there indication that this object is going to jump up? So what can you tell about the vertical axis? The net force on it is what? Which means, by default, what can you tell me about Fn and Fg? They must be what? You got it. That's it. So let's just write what? Everyone, let's just write next here. Let's say y-axis. Fn equals Fg. Fn equals Fg. What does that mean? Can I replace Fn with Fg here? That's the whole idea. See, my FBD told me exactly what to do with the equation. Awesome. So mu_s equals Fs over Fg. Okay. Every time you see Fg, what do you always replace it with? Every time. Grade 12, first year. Mass times G. Yes, so mu_s equals Fs over mg. What numbers do I know? Do I know the mu_s? Do I know the mu_s, which is the coefficient of static friction? Check. Do I know the mass? Check. I always know the G. Perfect. Crisscross and multiply. Done. So that means Fs equals us, which is 0.25, times the mass of the object, which is 110, times 9.8. Who's got this? Come on. Should be 250 something or 260. Exactly. Or, according to their answer, 270. By the way, what's the sig fig situation here? What's the only number that you, sorry, how many sig figs here? 2, because zeros in integers don't count. And how many sig figs here? 2, because leading zeros before decimal don't count. So 269 to what? 2 sig figs would be close to what? There you go. So you need to at least put in 270 newtons of work, not work. 270 newtons of what? Of no, newtons. I made the same mistake you made. Force. Thank you. You apply 270 newtons of force before you can see what? You can see it move. There you go. Anything less than 260 or 270, not enough. Not enough because the traction is bigger. 270 newtons. Done. Yeah, that's how much minimum you need to put in or need to apply with. All right. So let's go to the next slide, which is another problem. Okay. You are trying to slide a sofa across a horizontal floor. The mass of it is how much? 2.0 times 10 to the 2, which is 2 times 100, which is 200 kilograms. And you need to put in that much just to start it to move. Since that is how much applied force you need to put in to start it to move, it's also equivalent to what? If that's the minimum you have to put in, that's equivalent to what? The maximum the floor is pushing against you. Which means, is this technically the value of Fs? Yes, it is. Remember, Fs is the minimum you need to put in, which is going to be the maximum you're going against. Calculate the coefficient. Okay. Okay, everyone, do we need another FBD? Or can we reuse the same FPD idea from before? Yeah, FG goes down, Fn goes up, F applied is going that way, Fs is against me. All right, so mu s equals Fs over Fn. Again, Fn is equal to what? By the way, everyone listen up. A very common mistake. Listen up. A very common mistake. Many people think that Fn is always equal to what? Always equal to what? Except in two situations. Number one, when we have what? When we have ramps. You're going to have to do some trig work. The second thing is, how many forces do we have on the vertical so far? Only what? Yes, only two, which means Fg has to be balanced by what? What if I have 10 forces on the vertical? Is Fn now equal to Fg, or should I make a combination of them? Yes, so always be worried about what, sorry, always be concerned with what, if you have a slant, goes out the window. And if you have more than two forces, also goes out the window. You had a question. You had your hand up. Oh, you good? Okay. So, but in this situation, are we told anything of multiple forces or a slant? No, we're not, which means Fn could be safely substituted with Fg. Good. So, Us equals Fs over Fg. All right. But what did we say Fs is equal to in this case? Is it equal to applied force? Yes, because it just started to move. Remember, Fs is only equal to applied force once the thing starts to move, because that means the minimum applied just met the what? The maximum Fs. So you can say Mus equals F applied over Fg. And now we can plug in all the numbers we have. What's the applied force? How much force did you need to just start things moving? 350, because 3.5 times 10 to the 2. So 350. By the way, don't bother with newtons. Unless you know you're going to forget. What's the unit for Mus? No units, exactly. You want to prove it to yourself? Let's actually prove it right now. This is technically newtons. And what's Fg? Well, Fg is a multiplication of what and what? Mass times acceleration, which is like F net, which is also a newton. So the mass of the object is 200. And this is times 9.8. And the final answer here, not the final answer, I mean the value of this 200 times 9.8 will also be in newtons. What should happen to the newtons? Bless you. They have to cancel out, because that's how dimensionless coefficients behave. Boom, done. That's it. All right. What's 350 times, sorry, divided by 1960? Yes. To 350 divided by 1960. Right? Yeah, 1960. Because I have to get a decimal less than 1. 0 point. What's the specific situation? 2 and 2. So what is it? Sorry, 0.18. Yeah, 350 is about 1/6 of that. Okay, yeah, I think that makes sense. How many of you got 1/8? Great, it is 1/8. Okay, everyone, pencils down. So let's just take this out. Height and okay. First of all, let's make the angle what? 0. So you're perfectly pulling this way. By the way, we're gonna do tilted tension forces, but let's just do the easy one today. Okay. Question. Let's say the mass, everyone. Let's say the mass is 3.5 kilograms. Okay. Now, I know the mass. To know how much force I need to start it to move, I also need to know what? By the way, do you see the roughness of the surface? So what do I need to know? The what of static friction? No, I already know the mass. I know the mass. I said the mass to be 3.5 kilos. But what do I need to know about the surface? Not about me, about the surface. The coefficient. By the way, everyone, look. Check out what's going to happen to the. What do you think is going to happen to the roughness of the surface if I increase the coefficient? Is it going to get smoother or rougher? There you go. You got it. The Mus and Muk's are just indications of what, of the roughness of how two surfaces interact. Look. Yep. How about if we make it lower? What about 0? Exactly, no friction. Perfect what? Perfectly no traction. Okay? So Junan, give me a value you want for the coefficient of static friction. Remember, you have to go by the three features, right? Has to be positive and has to be less than 1. So basically, give me a decimal, any decimal you want. 0.7. All right. See how the roughness is going. Okay. Can I now calculate how much force I need to start it to move? Did we just do 2 problems like that? Yes, we did. Okay, everyone. Tell me what we did for the first problem. Come on, come on. Tell me what we did for the first problem. Go. Look at the first demo problem. What did we end up doing? Did we end up dividing or multiplying? We didn't end up cross multiplying. Okay. So let's actually what? Let's do that right here. Okay. What was the equation anyway? Fs equals, come on, Fs equals what? Mu times Fn, right? But Fn in this case is equal to what? Fg. And Fg is equal to what? You got it. All right. Let me multiply. What's mu s? Janan, what number did you choose? You said 0.7. 0.7. What's the mass that we set? 3.5. And g is what? 9.8. Okay. Someone do this as well with me just to check that my answer is correct. 0.7 times 3.5 times 9.8. How much? 24.01. So that means what? If I push with a 23 newtons, is that going to be enough to move it? How about 24, technically? No. 24.01. Technically still not, because you just what? You just canceled. Anything more, we'll get it to what? We'll get it to what? To start moving. Okay, everyone, eyes on the screen. What's this word? Tension, as if I'm applying a tension force. Okay, let me zoom in, and let's see what's going to happen. All right. Okay, how much is my tension so far? Okay, wait a minute. All right. Okay, keep going, keep going, keep going. Again, I need how much? 24. Yeah, what just happened? It acquired what? It acquired acceleration. Before that, what was the acceleration? 0, which means what? No motion. Exactly, that's it. How about if I increase this guy? How about if I increase it to 1.5? Do you think I'm going to need less applied force, same or more? Yeah, it's getting rougher. I need to apply more force. So what do I do now? Instead of 0.7, I use what? 1.5. Okay, how much is that? 1.5 times 9.8 times 3.5. I need to up it to what now? About 52 newtons. All right. 52 newtons. Okay. Almost, almost, almost. Okay, everyone. Tell me when you start seeing what? A non-zero number here. How much did I hit? 51.5. Apparently, I needed how much? Is it making sense now? You just need that minimum. And depending on how much you actually get extra, you get what? More or less acceleration. Hello. What's up? Shoot. You can ask them. That's how good they are.
I feel like I should know this.
Okay.
So we're rearranging. This is the refractive index, and then that's the speed of.
Can I show it here?
Yeah.
All right. So what do you have? Go.
Okay.
By the way, she's doing something we're going to do in the light unit. And how many people have heard of index of refraction? Yep.
That is what we're talking about.
So index of refraction is N equals what? C
C
over V.
Yep.
Okay.
And we are given N.
C is the speed of light in vacuum.
Yep.
And V is the speed of light in the glass, in the
medium,
yes.
Yeah.
So apparently, what do we have?
Has a refractive index of
1.46. So
Yeah.
that's this guy equals.
And then we've got the 3.
What's this? What's the speed of light in vacuum? Come on, famous number. 3 times 10 to the. No. In meters per second, it's what? لا. Come on. That's kilometers. What is it?
3
Times 10 to the.
times 10 to the power of 8.
8 meters per second. 5 if it's kilometers, 8 if it's meter. Super fast.
Divided by V.
How do you solve this? I'm not going to say anything. Come on, people. Cross multiply.
Right.
Chris,
Okay, that's what I thought.
cross. So,
I think that's what my student was trying to do.
yep. Cross multiplying. So 1.46 V's equals 3 times 10 to the 8.
Yeah.
And then what? How do you clean this up? Divide both sides by 1.46, 1.46.
That's the step you
Yep.
step on.
Those two cancel, so you get the v that you want, and then you go 3 exponent 8 divided by 1.46. Obviously, nothing could be faster than speed of light in what? In vacuum. So makes sense. When you divide by anything bigger than 1, you go lower. It's still going to be super fast to our senses, but according to what? To a sensitive machine, it could be measured 2.05 times 10 to the 8, which is less than 3 times 10 to the 8. Done, done. No problem. Anytime. All right. Okay. So, oh, everyone, look what's okay. Which one did we say is always bigger, mu s or mu k? Mu k. Sorry, mu s. Which means this could never be bigger than what? Which means I could increase it. Do you see what it sets its maximum value to be? This will never go beyond this. Which means what? If I decrease this one, this has to decrease as well. You see? It could never be more than it, but it could be anywhere less than it. I could increase this one, and basically now it's giving me a higher spectrum to go all the way up to 2, 3, 4, whatever. By the way, it's very rare to see them what? More than one, but it could happen. It technically could happen. Okay? Does that make sense? All right, so whenever you want to know how much force you need to push a fridge, you need to know two things about the fridge. Well, you need to know one thing about the fridge, which is what? Obviously, its mass, how heavy it is. What's the thing you need to know about the surface of the floor and the fridge? Exactly, the what? The coefficient of sacrifice. And once you know these two numbers, what can you do? You can multiply how rough the surface is, how heavy the object is, and obviously what? How much the gravity is pulling down by acceleration, which is 9.8. Once you know that, you will know if you should bother with what? With pushing it or not, provided that you can put in that much applied force. Okay? All right. Let's do another link. 1 second. Okay. This one. Yes. Everyone, look at this one. Let's just select all. 1 second. Okay, everyone, eyes on the screen. So, begin. Yes, here. Okay, everyone, look at this. Look at this animation. If you keep clicking on type of surface, you change things. Rubber on ice, aluminum on steel, glass on glass, and so on. Okay, then you can do the what? The object mass. Okay, apparently it goes up to 2 kilos. Okay, no problem. Let's say you got to here. Exactly, in grams. Yes. So the question here is what? How much force do you need to put in to what? To get a wood on what? On lab table, which could be this or whatever. Okay, everyone, we're gonna do this. Let's start. So I'm gonna say start. Okay, everyone, I want you to focus on one thing first, and then I'm gonna get your attention to this graph right here. I'm gonna show you what happens. So let's go. Start. Increase, nothing. So apparently, let's do it again. When they start moving, whenever those start, 3 point. Okay, I'll tell you why. What did we say? Which one needs more force, static or kinetic? Which means once you start something moving, do you need to keep that high force or can you go low? There you go. Apparently, it kept going up to what? 7. And once it started moving, they what? They lowered it to what? Apparently, how much? Okay, check this out. Everyone, ready? There you go. Check this out. There we go. Can someone explain to me what this graph means? Exactly. Apparently, as time, okay, as time started going by, what happened to the force? They started what? Basically, that's me going like this, right? That's me going, increasing. But once they hit almost how much? 8, it started moving. So what did they do? They slowed, or not slowed down. They basically what? Almost instantly. What did they do to their force? Keep it or shrink it? They diminished their force, and then what? Kept moving at a constant velocity. Obviously, you did not need that high force to keep happening, because then the object would keep accelerating. No, I'm gonna up it, go below to keep it what? Constant speed. Have you ever tried to push something and you're pushing and you're pushing and you're pushing, and once you start, what happens to you? Right? Why? No, but why? Because you were pushing with a high force, and then what happened? It basically skipped. Did you need to go that much force? No. Immediately what? Go down. Exactly like that. Does that make sense now? Yes, that's why. Let's do another, for example, another surface. Oh, sorry. Reset. Yes. Let's go rubber on ice. What do you expect with rubber on ice? High force or low force? Oh, in general, force. Okay, let's see. The same mass. Again, control experiment. You only change one thing. Apparently, it took only how much? 1 point something. Let's see the graph. Yep. All it took is how much roughly? Between roughly 1.75, 1.8, and then it took this much to go into kinetic friction, constant motion.